So welcome everyone. Thank you for coming. If you weren't here for the announcement a second ago, make certain you have pen and paper handy because we will have some examples to work on today. And I'm going to go ahead and turn this over to Benda to get us started.
Thank you, Marissa. What a wonderful introduction. Thank you so much. So let's see. Let's start with me, Benda. So this is part 2 of our Get Inspired webinar series for calculus. My name is Benda Ngandu, in case you were not here for part 1. We will be going over limits during part 2. But just as a recap, I did want to review that if you did not see part 1, I would highly suggest watching that. Part 1, we went over what is calculus, why is it important, and why you would be taking it. But like I said, my name is Benda Ngandu. I am the Center Director at Mathnasium. I'm Midlothian. Midlothian is an area outside of Richmond, Virginia. I know we may have some people who's not familiar with the area, some people around Virginia, some people maybe even outside of Virginia. But what we do at Mathnasium is we are a math-only learning center. We focus on students from 1st grade to 12th grade to help their math abilities to get them ahead, but also to catch students up as well. But one of the topics that we help students with, which is not very frequent because it's not a very frequent class overall in Virginia, but calculus. I will say my area, Midlothian, we have a lot of high achieving schools and advanced placement schools. So we do have a big concentration of calculus students. I was actually raised in the Chesterfield County area, which is what Midlothian's in. So I am familiar with how many people take calculus, but I know that does vary from county to county, city to city, state to state, and whatnot. But like I said, please refer back to part 1 if you want to refresh on what calculus is and some techniques about what you can do to actually prepare yourself for calculus outside of attending these webinars. So let's go ahead and get started. So like I said, we're going to be talking about limits, but I wanted to mention the name of this, which is the limit does not exist. If you do not know why that is in quotation marks, you are probably very young. But we are going to be evaluating a limit from a very popular movie I will mention towards the end of the webinar, if I remember. So we can talk about math and pop culture, because it doesn't happen that much. So we have to immortalize it. So first thing I want to talk about is, just like anything in math, math has foundations. Math has layers. We need to make sure we are having a strong foundation in our math so we can make sure we have long-term success in the next level. And this applies to things as low as 1st grade addition and subtraction. So of course this will apply to calculus. Before you should take calculus, you would take a pre-calculus class or trigonometry class or a combination of the two. So these are just a few, not all, of the prerequisites I would definitely suggest you look over and review if you're not comfortable with them before you actually dive too deep into practicing limits. What we're going to be doing today is only a 30-minute session at most, and it's not going to be a full class per se on limits. I just want to hit the sweet spots and then give you some resources to practice on your own. But if you do not feel comfortable in these 3 areas, and then there's sub areas as well, I would highly suggest you find resources, which I can also mention to you at the end, to go over this before you even dive into limits. So what is a limit? So sometimes in math, we can't always evaluate functions. If you take an algebra 2 and then also in trigonometry, there are always some questions where you do all the math, and I know if you're anything like me, you get upset because you get all the math and you don't get an answer, or your answer does not exist, or there's no solution. So in calculus, what we use limits for is to see what the function is approaching. So I know sometimes with functions, we should always have answers, but when it comes to limits, this gives us the opportunity to expand on functions that don't have solutions at a certain point. But whenever you hear the word limit, I want you to think about approaching, because that's going to be part of the notation we're going to go in a second. But whenever we hear about limits, we're seeing, okay, what are we approaching? What is our input or our range approaching when we're trying to hit this domain? From both sides, I should say. But why are limits important? Well, first, limits is the very basis, I would say, of calculus, and it's going to help define continuity, derivatives, and integrals, which we will maybe go into in later parts. but we're not going to talk about much of the derivatives and integrals today. We might touch on continuity. And this is what limits are known and used for. And limits are kind of a small part. This is typically the shortest unit, I would say, in calculus, but it's something you're going to have a good foundation in because it's going to show up in every other unit in calculus. So I'm going to switch to my handy dandy whiteboard with my handy dandy, I forgot what this thing, Wacom board. All right, what were we talking about? Limit notation. So I just wanted to explain the different parts of a limit. When you see an example, this is just a kind of, oops, let me write it down here. This is kind of a, I guess baseline, you can say, of how you would write a limit. Wow, that looks a lot worse than it usually does. But hey, let's read it. So what we're talking about, hopefully you can see my mouse I'm hovering over, but the LIM, of course, stands for limit. But I want to point your attention to below the LIM, where we see X and then this little arrow, and then we see the A. So that is saying X approaches A. Remember, whenever we want to talk about limits, we want to think about the word approaching. So whenever we're talking about X is approaching A, usually A is a constant. A does not always have to be a constant, but we're not going into that right now. But typically you'll see A as constant. So X can be approaching 0, X can be approaching 2, X can be approaching negative 56, X can be approaching pi over 4, or whatever you get. And then what we're looking for when we're evaluating that limit is what is the X approaching, what is the limit of f of X as X is approaching A? So what does that mean? As you should already know, X is the domain, X is what we put into our function, and then Y is our range, or what our output is of the function. We want to find out what is the output approaching as our X value is, or our domain is approaching a certain value. And it usually is equal to something. I just said this is equal to 0. So that is the limit notation. So you're going to see a lot of that as I go through the examples. So now I'm going to stop sharing and then reshare, so I don't mess up anything. So now I want to point your attention to the bottom of this screen because there is another aspect to the notation that is very important. So here you see the limit as X approaches A, and then you see a minus sign. And then if you look to the right of the picture, you say the limit as X approaches A, but then you see a plus sign. If you didn't already guess by the picture, when we say minus, that means we're coming from the left of the function. And then when we say plus, that means we're coming from the right of the function. What I like to use to remember that is that when we have a minus, think of it as negative infinity. So we're looking at the domain approaching from negative infinity, which is X. So that's coming all the way over here from the left side. And then we're going up the function. And then we're going to look at it from positive infinity on the right side, and that's how we get up here. So that's what's called the left-handed limit and the right-handed limit. So as you see here in this example, this picture, when we're looking at constant X equals A, from the left side, our function is approaching 3.8. From the right side, our right-sided limit is approaching 1.3. Whenever we have a right-sided limit and a left-sided limit that do not equal, that means the limit does not exist. So that is an example of today's title of this webinar, the limit does not exist. Sometimes you do all the work and you technically don't get an answer, but does not exist is an answer. I did also want to showcase, I guess I don't have to write it out, but typically does not exist can be abbreviated as D&E, usually capital D&E. So just be aware of that. So now we're going to switch to Desmos. So for you guys who don't know what Desmos is your best friend in high school typically. I can definitely say that as far as the Richmond area. Desmos helps with a lot of things going up into algebra and above. And this really helps to explain limits, because what it basically is an online graphing calculator. So you don't have to go and buy that, TI calculator that's like 60 plus bucks. Which is 60 is probably like the cheapest you'd be able to find a new one if you're lucky. And Desmos is free to the public. You can even make your own account through it. You don't really have to. but it is free to the public, and I would highly suggest you guys use this to prep for your calc courses. But I will say, do not use Desmos as a crutch. You are not always going to be able to use a graphing calculator, and even if you are able to use a graphing calculator, usually you have to use an actual calculator. You won't have access to a actual Chromebook. So I have an example here, and what we're looking at is the function y equals 5x squared. You can kind of see that by this part up here on the screen. So this is the graph. Like I said, Desmos is a graphing calculator. I could literally just rewrite it, and it's going to show up again down here, and it graphs our function. But I wanted to show you guys this cool feature that Desmos has, and it's a table. So with the table, you can input anything you want as far as your domain and see what your range outputs. Let's say we're trying to evaluate the limit as x approaches 1 of the function 5x squared. So I kind of talked about how limits are basically used for when, are mainly used for when we do not know the actual value, so we have to see what it's approaching. I think we all know what f of x squared is when we plug in 1. I'll pause. All right, I heard you in the back. You said 5, correct, because when we say 1 squared and then we multiply it by 5, our output is 5. And you can see that in the middle here. When we plug in x, we get 5 out. But we are going to be using limits to, find answers that we can easily find, just by doing the math, whether in our head, on paper, or with a calculator. But this is just to get the idea of what a limit shows. So when we're talking about limits and we're talking about left-handed and right-sided limits, remember I talked about if the left-handed limit and the right-handed limit do not equal, that means the limit does not exist. So what we're going to do as we test as x approaches 1 is we're going to see how close can we get to 1 and can we approximate, in case we didn't know that when we plug in 1 to 5x squared, we get 5. Let's see how close we can get to 1 without touching it from the left side, and then how close we can get to 1 from the right side and see how we can get. So let's talk about from the left side. So as we said, the left-handed limit typically says as x approaches 1 and there's a little negative, that means we're coming from negative infinity as far as our x-axis. So that means we're going to come all the way from this direction. We're going to kind of look at this graph. We know it's going down, we haven't gotten to x minus 1 yet, but then when we pass 0, it starts going up, and then it looks like this is 1 right here. It looks like we're at somewhere between 4 and 6. So we know 5 is directly into 4 and 6. So it's probably 5, right? Let's say we don't know that. When we plug in 0.9, we get 4.05. That's pretty close to 5. 0.99, we get 4.9005. That's a lot closer to 5. 0.99999, we get 4.99, blah, 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 blah. So as you can see, the closer we get to 1, x equals 1, the closer we get to y equals 5 from the left side. So I will say the left-handed limit is equal to 5. Now let's approach it from the right side. So let's say we're up top here, and we're looking at just when x equals 1.01, and then we go to 1.01, and then 1.001. You see it go from 6.05 to 5.1 to 5.01, and I could keep going on and on and on. And we'll see from the right side that it will approach from 5 as well. So that means that the total limit, since the right-handed limit equals 5 and the left-handed limit equals 5, together that total limit equals 5. Mind you, we already knew that, but that's a good way to check our answer, that we know we could plug it in algebraically, get our 5 out, and then that way we can make sure that our answer is correct and not just, trust the limit, I guess, even though you shouldn't. All right, so if you're anything like me, especially if you're a math person, you love flowcharts. I'm sure I have some STEM people out there, especially you engineers. Flowcharts are life, maybe even for your programmers too. But I will show you where I got this flowchart from, but I really like it because with anything in math, think of math as a toolbox, and you want to make sure you have the right tools. But some of your tools are not necessary for certain jobs. My favorite example of that is a lot of times in algebra, when we're trying to find the answer to a quadratic equation, let's say it is x squared minus 4. a lot of people pull out their favorite or most hated tool in their toolbox, which is the quadratic formula. Ooh, Marissa, I should have brought that meme out. I love that meme. I should have brought that. That would have been perfect. But quadratic formula is not needed for a function such as x squared minus 4. Since I know all of us have taken up to at least algebra 2, you know there's a such thing as difference of squares, and then we can factor it out, and then we know that our zeros there are x equals 2 and x equals negative 2. But we don't need to do the whole quadratic formula, the whole negative b plus or minus the square root of b squared. We don't need to do all that for something like that. So what I really like this flow chart is that we want to see, you know, what's the easiest thing I can do first? And then if that doesn't work, what can I do next? So the first thing is direct substitution. So as we kind of talked about before with that 5x squared, we knew when we plugged 1 directly into that function, we would get 5 out. Therefore, the limit would equal 5. Will that always work? No, but when it does, it's nice, quick and easy. You know, that's as simple as going back to algebra 1. So I do want to go over this when there is some examples. So sometimes we have a function where we are dividing by 0. So we cannot divide something by 0 because back to algebra 2, we talked about domain restrictors, and that's one of the two. So when we're looking at the limit as x approaches 1 of 1 over x minus 1, when you plug 1 into that function, 1 minus 1, of course, equals 0, and we cannot do 1 divided by 0 because that is an undefined function, or undefined value, I should say. So direct substitution does not work in that case, but we can talk about what could work later on. In this case, most likely the limit is found because we can just plug in that limit into the function. Mind you, going back to this notation, the limit as x approaches a of f of x, when we do direct substitution, that's just equals f of a. So if we get f of a, that means we get a number, we get a constant, or we get, you know, some type of value, and then that's our answer. Or there's this another thing called indeterminate form, which I know is gone over in algebra 2, but very briefly, some people may not remember it. Sorry, not algebra 2, pre-calculus. Some people may not remember what this means, but basically, when we plug something in, we have 0 divided by 0, which is an indeterminate form. And we're not going to go into how to solve that today, but there is a rule with when we get to derivatives that we can talk about by this cool French guy whose name looks like hospital. Let's go back. No, wrong way. Aha. So let's say we went to, we tried all of these and none of them worked. So the next step would be, let's try to factor it. So just like in this indeterminate form here, x squared minus x minus 2, we're dividing that by x squared minus 2x minus 3. What happens if we factor the top and factor the bottom? I'll tell you what happens. The x squared minus x minus 2 will factor into x minus 2 times x plus 1. And then the denominator would factor out to be x minus 3 times x plus 1. So let me actually write that out so we don't get lost. So I may have messed something up. Let me see if I remember it. We have x squared minus x minus 2 all over x squared minus 2x plus 3. No, I think the plus is wrong. Let me look. Minus 3. Undo, undo, undo. Minus 3. So like I said, when we factor this, this is a pre-calculus prerequisite, so I'm not going to go into how I factored it. At the top, we get x minus 2 times x plus 1. Now in the bottom, when we factor that, we get x minus 3 times x plus 1. Now we got something that looks a little bit better, but what do we do next, Benda? I will tell you. So we see something common in the top and we see something in common in the bottom. Whenever we do that, cross it out, cross it out. So now look at that. We have a lot less to work with, but more importantly, do we have something in indeterminate form? When we plug in, I think x was approaching 1. Yes, when we plug in 1, 1 minus 2 equals negative 1, and in the bottom, 1 minus 3 equals negative 2, so we get a constant of 1/2. That is not indeterminate form, therefore that is the value of our limit. Mind you, does that mean that when we plug 1 into that function, it equals 1/2. No. So let me show you why. X squared minus x minus 2 all over x squared. See, isn't it cool that when you start typing, even when you're done, it starts just throwing stuff at you? I love it. So we're talking about as x approaches 1. So we're gonna look at this graph. If you don't know anything about rationals, typically you have a horizontal and or a vertical asymptote. But let's use the table. That's what I should do. So as we look at -1, let's see. So as we were talking about with when we factor something out, canceled out the x plus 1 in the top and the bottom. So whenever we cross something out, if you go back to algebra 2, there are these things called holes. So holes is literally when you just put a hole in the function of where something looks like it should be there, but it's not. So as you can see here, as we're approaching -1, it looks like from the left side and then from the right side, or backwards, from the left side and from the right side, it should be whatever this is, which I'll tell you should be 1/2. So when we look there, it looks like it's filled in, but when we look at the graph, it's actually an undefined function. So that is because something cancels out in the top and then something cancels out in the bottom. So therefore we have a hole, or in calculus, we call it a removable discontinuity. More on discontinuity in our next series. But that is what we use limits for, because like I said, that is an indeterminate form, but we were able to factor it and then get an answer to make sure that we could find out at least what it approaches. Other things to go over, which is kind of from prerequisite pre-calculus that I talked about earlier, is talking about conjugates and then talking about trig identities. So you should have just taken pre-calculus or trig if you're going into calculus either this summer or into the fall. Either way, I would highly suggest you start reviewing your trig identities, which you should typically have memorized. Like the most basic one is sine squared plus cosine squared x plus cosine squared x equals 1. That's just one of the many. So I would highly suggest you go through and review those, memorize those, because we want to have that down pat. Because you're going to be, you need to have those right off the bat kind of fast, like you used to have your multiplication facts. Hopefully you still have your multiplication facts real fast like that. And as well as conjugates, that's just an algebra method of solving something. So we're not going to review that because again, that is a pre-calculus prerequisite. But that will lead me into my next point, since I know we're coming to a close. I do want to reveal with you guys some good resources, online, free resources that are out there on the web. So number one thing is Desmos. You see how it works. We talked about it. But one of my favorite things, and one thing we use a lot at Mathnasium, especially for higher level math, is this website called CUDA. So I can definitely speak for my local county that a lot of teachers love CUDA as well, because it is a software where teachers are able to make different worksheets to, change things up, make sure, people aren't copying notes or whatever, and to make quick answer keys as well. So there's a software that typically teachers pay for, but there are free worksheets that CUDA provides, which these don't change. These are pretty standard. But what I really love about them is that, one, it goes all the way back to pre-algebra and all the way up to calculus. So even if we're just reviewing our pre-calculus stuff, you can even go into calculus and practice some things. And it won't show you how you get the answer, but it will give you a good chunk of questions, and it will give you the answer to check behind yourself. So if you didn't notice, this is page 1 through 12, and then on page 2, 1 through 12, I'll have these red answers. So that's definitely a lot of free resources you could have on a various of topics. If we just look on this calculus page alone, it goes into a lot of things. The top first two things are limits and continuity, and then we're going to go into a lot of other things, but then it goes into a lot of other things that calculus goes into. We will not go all the way up into integration. But I also wanted to show you, there we go, where I got that flow chart from, Khan Academy. So I'm sure a lot of you, high school and college students are familiar with Khan Academy. It is a pretty good free resource to use for higher level math. But this is where I stole that flowchart from. I shouldn't say still, borrowed that flowchart from. So we will make sure that, Khan Academy will make sure that you have a lot of practice problems as well. And they do a little better of a job of actually giving you solutions and how to work your answers to the solutions. But it's still very limited too, especially because, calculus is a very broad subject and not a lot of people do calculus. So you are a rare breed, I will tell you that. But these are just some other examples of what CUDA actually provided. Sorry, I forgot to go back. Like we talked about holes, it gives a good representation of holes on this, and then other things like just plugging in the function, as well as piecewise functions and whatnot. So that ends that. So we are done. No, we're not done. I need to go over the quote I was talking about. Oops, wrong screen. Or is it? What do you see, Marissa?
Okay, it's there now. I just took a second.
Okay, there we go. Let's see. So as you can see, there's Lindsay Lohan here. Lindsay Lohan, star of Mean Girls movie. It came out in like 2003 or something. Very, very big in pop culture, at least back in my day. I talked to some of my high schools about it now, and they're like totally clueless. But that's okay. Clueless, another pop culture reference. But nothing to do with math. So let's go back to Mean Girls. So in Mean Girls, not going to go over the plot, but Lindsay Lohan here is on the math team, or whatever they call it. And they're battling this other nerd school. And they come to this example. And in the midst of her having a teenage life crisis, she is able to solve this math problem, even though she did not pay attention in math at all that year. So this limit looks a lot of complex, especially compared to the ones that we went over today. We weren't going to go too in depth, not much I can do in 30 minutes. But the very popular phrase that came from Mean Girls is the limit does not exist. So we just talked about what that means. The limit does not exist. And I just wanted to show you what the question is. So mind you, this says the limit as x approaches 0 of natural log of 1 minus x minus sine of x all over 1 minus cosine squared x. There is another way of doing this, and I will talk to you about it while I switch screens. Power series approximations. We are not going to go into power series. Typically, even math people don't like using power series approximations for limits. It's typically an engineering thing because engineers are lazy.
I'm offended by that statement.
That is true. Engineers, I mean, you guys got a lot going on, so you have to make life as simple as possible. So we're not going to go into that, though. What I will show you is just the graph of this function. So that same graph from the Mean Girls question is listed here. And here is our Desmos graph. Remember, Desmos is a powerful tool. And we're looking at it as x approaches 0. So as we can see here, the left side of our limit, as I zoom out, at x equals 0 is going all the way up, all the way up. It's going as high as it can, and it's never touching anything. That means it's approaching positive infinity. Yes, limits can approach infinity. And then if we look from the right side, we see the function going, go all the way down until it will never stop. Sorry. And that goes into negative infinity. So does negative infinity equal positive infinity? No, it does not. Therefore, the left-hand limit and the right-hand limit do not equal. Therefore, the limit does not exist. And with that, I will close. Actually, not with that, Marissa. We will briefly go back to the PowerPoint because I did want everyone to know that next week's show will be on more limits, but also going into continuity for part 3 of our calculus series. So now can go into any questions that we might have.
So we do have at least one question just starting off, and this was about future topics, like you might have covered a little bit now. It says, will there be a webinar on the indeterminate form or algebra 2 topics?
So this series is primarily on calculus. So we don't really want to go over those prerequisites. I kind of just want to go over the core calculus. Actually, Marissa, sorry to put you on, put you on the spot live, but someone did ask me, how can people, request webinar topics? Is there anything possible for that?
So they can definitely reach out via email to any of our centers. So if they've been to a previous webinar topic, they can reach out that way, and if they're on our list. Otherwise, if they like talk to a center director, y'all can definitely pass that information my way, and I will see what we can do and see if we can find any volunteers to run that topic. I would say that they could also probably comment on YouTube and just say like, hey, I'd like to see this, and I'll see those comments.
Yes, she will, because Marissa sees all.
It's my job.
Mathnasium wise.
So yeah, and questions that I had already answered before this, just so you know, Benda, if you wanted to add anything, is we had a question about the flow chart being available online, and you then answered that by showing us where it came from. And then we had a question about, do we use Khan Academy as part of our program?
So Mathnasium, no, does not use Khan Academy as our program. Khan Academy is its own thing, but it is a free online resource. I have people who do Mathnasium with us, whether that's online or in person, and they also do Khan Academy to get ahead and just to have exposure with some things. So if you want to, feel free to go ahead and use it. But no, Mathnasium and Khan Academy are not associated with each other, as I'm sure Marissa already told you.
I did, but just in case you wanted to add anything, I will add, I've definitely seen some high schools in the Richmond area that like to assign Khan Academy as homework. So that might be the kind of thing that you're seeing in school, is you might be working through some of those modules on your own.
I second that.
Thank you again, Benda, for this topic and all of this fun calculus knowledge.
Thank you, and thank everyone for attending.